All right, let's talk about the universe's most mind-bending objects, black holes. I mean, these things are wild. They're not just empty spots in space. They are the absolute final act for the biggest stars out there, and they pretty much throw the rulebook of reality right out the window. So that brings up a couple of big questions, right? First, where in the universe do these things even come from? And, the one we all wonder about, what would actually happen if you fell into one? Let's get into it. The funny thing is, the story of a black hole doesn't start with darkness at all. It starts with an incredible amount of light. It all begins with a star, but not just any star. A star so ridiculously massive that it's basically destined to die in the most spectacular way possible. So what is a star really? Well, at its most basic, it's just this giant cloud of hydrogen gas, and there's so much of it that its own gravity starts crushing it inwards. That pressure gets so intense at the center that it kicks off nuclear fusion, and that is the engine that makes a star shine. For most of its life, a star is in this perfect, stable balance. Think of it like a constant cosmic tug of war. On one side, you have the unbelievable force of gravity, trying to crush the star into a tiny ball. But fighting back with equal strength is all that energy from fusion, pushing outward from the core. For billions of years, it's a perfect stalemate. But for the real monsters of the universe, the most massive stars, that balance can't last forever. Eventually, something has to give, and when it does, it leads to a final, catastrophic moment of collapse. And the culprit, the thing that brings it all crashing down, is iron. See, a massive star spends its life like a factory, fusing lighter elements into heavier ones. It turns hydrogen into helium, helium into carbon, all the way up the periodic table. But the process hits a dead end at iron. Fusing iron doesn't create energy, it actually takes energy away. It's a total showstopper. So you can imagine what happens next. The star's core gets clogged up with this useless iron ash. The fusion engine sputters and dies. The outward push just stops. And with nothing holding it back, gravity wins. And it wins instantly. In less than a single second, the core collapses at a quarter of the speed of light, and the outer layers of the star rebound in this ridiculously huge explosion we call a supernova. What's left behind is either a neutron star or, if the star was big enough, a black hole. So, poof, we've got our black hole. But what even is that thing? Let's break down the two parts you always hear about. First up, there's the part we can kind of picture, the event horizon. It's best to think of this as the surface. Now, it's not solid or anything. It's more like a boundary line. It is the literal point of no return. Once you cross it, you'd have to go faster than the speed of light to get back out, and, well, that's impossible. It's why it looks like a perfect black sphere. It's a one-way door in space-time. But deep inside, at the very center, that's where the real mystery is, the singularity. And I'm going to be honest with you, nobody knows what it actually is. Our best physics says it's a point with zero size, zero volume, but it contains all the mass of that dead star. It's where our understanding of the universe completely breaks down. It really is like a dividing by zero error in the fabric of reality. And hey, let's just clear up a huge myth right now. Black holes are not cosmic vacuum cleaners. They don't just go around sucking everything up. Their gravity is immense, for sure, but only when you get really close. Here's a fun fact. If you replaced our sun with a black hole of the exact same mass, Earth would just keep orbiting it like nothing happened. We'd, freeze, but we wouldn't get sucked in. Okay, so we know how they're born, and we kind of know what they are. But what about that other question? What if we could actually take a trip into one? What would that journey be like? Well, this is where things get really, really weird. Because the first thing to break is time itself. So, let's say your friend is watching you fall in from a safe distance. To them, you would seem to slow down as you got closer to the edge. You'd get redder and dimmer, until you looked like you were frozen in place right at the event horizon. And then you just fade away. But for you, from your point of view, you'd see the entire future of the universe play out in fast forward. So what happens after you cross that line? Well, the first theory for your fate is not pleasant. It's got a great name, though, spaghettification. The gravity pulling on your feet would be so much stronger than the gravity on your head that you would be stretched and stretched and stretched until you were pulled apart, atom from atom, into a glowing hot stream of plasma. Yeah, not a great way to go. If that doesn't sound good to you, there's another theory. Some physicists think the event horizon itself is actually a firewall, a wall of insanely high energy particles. So in this version, you don't even get to fall inside. The second you touch the event horizon, you just hit this wall and are vaporized instantly. So, pick your poison, I guess.
Now, which horrible fate you'd meet actually depends on the black hole's size. If it's a small one, just a few times the mass of the sun, the tidal forces are so intense you'd be spaghettified way before you even reach the edge. But if you fell into a supermassive black hole, like the ones at the center of galaxies, the edge is so big and the curve of space-time is so gentle that you could actually cross the event horizon totally fine. You could float around in there for a while before things got stretchy.
And when I say supermassive, I mean it. That might even be an understatement. The biggest one we found so far, a beast called S50014 plus 81, weighs in at 40 billion times the mass of our sun. To try and wrap your head around that scale, its diameter, just the black part, is 47 times the distance from our sun all the way out to Pluto. It's a monster, a true cosmic leviathan. But here's the final twist. Even these monsters, these things that seem like they'll last forever, they don't. They have one final chapter, and it ends not with a whimper, but with one last spectacular bang. Get this. Black holes aren't actually permanent. They leak. It happens incredibly slowly, but they lose their mass and energy over time through a process the brilliant Stephen Hawking figured out. And, fittingly, we call it Hawking radiation. Okay, so how does a black hole leak? Well, turns out empty space isn't really empty. It's fizzing with these little pairs of virtual particles that pop into existence and then disappear almost instantly. But if a pair pops up right on the edge of a black hole's event horizon, one particle can fall in while the other one escapes. The one that gets away becomes a real particle, and to do that, it has to steal a tiny bit of energy, which means a tiny bit of mass, from the black hole itself. Now, this is a mind-bogglingly slow process at first, but it speeds up as the black hole gets smaller. When it shrinks down to the mass of an asteroid, it glows about room temperature. Get it down to the mass of a mountain, and it shines with the heat of the sun. And then, in its very last second of life, it goes out with a bang, exploding with the energy of billions of nuclear bombs. But don't hold your breath waiting for this final fireworks show. For the biggest black holes out there, the evaporation process will take a Google years. That's a 1 with 100 zeros after it. It's a timescale so long that the entire current age of our universe wouldn't even register as a blip. And that leaves us with one last, kinda haunting thought. Way, way in the future, long after the last star has burned out and the universe is just cold, dark, and empty, these final explosions will be the last interesting thing to ever happen. Which makes you wonder, who or what will be around to see it?